Welcome back to the Deep Dive. This is where we take a monumental stack of sources, articles, and data, and we boil it all down to the essential knowledge you need right now.
It's all about that intellectual shortcut.
Exactly. For anyone who wants to stay deeply informed but, doesn't have time to read everything, this is for you.
And today's topic is, well, it's fundamental. It's the absolute bedrock of all modern technology.
We're talking about open source software. And more specifically, we're going deep on the container images that power, pretty much every production environment on the planet.
It's a topic that's just so critical right now because the speed of everything, of digital transformation, it means that organizations aren't just building software anymore.
No, they're assembling it.
They're assembling these incredibly complex supply chains, and they're built on open source components that, honestly, are often treated like black boxes.
So our mission today is to crack open that black box. We're going to be analyzing the latest findings from Chainguard's The State of Trusted Open Source report.
And we really need to identify two things. First, what are the foundational pieces that, everyone is using? But then, and this is the urgent part, where is the real security risk actually concentrated?
And I can promise you, if you are an engineer, if you're a CISO, or even if you're just curious about what's keeping development teams up at night, we are going to deliver that aha moment today. You're going to find out where the vulnerabilities are really hiding.
It's not where most people think.
Not at all. Okay, let's unpack this. Our source material today is just incredibly robust. This isn't survey or an opinion piece.
No, it's a quarterly pulse on the entire open source software supply chain, and it's all grounded in real-world usage data.
The scale is staggering. Chainguard analyzed anonymized product usage and vulnerability data from a catalog of over 1,800 container image projects.
And within that, 148,000 unique versions.
And get this, nearly 500 million builds. So this isn't theoretical. It's a ground-level view of what is actually running in production right now.
That volume of data is what lets us move past, just anecdotal evidence. We're tracking the real gravitational pull here. What are people actually using and how often?
And the window for this analysis is really recent.
Very recent. It covers the 3 months from September 1st, 2025 through November 30th, 2025. And in that short time, they tracked 10,100 total vulnerability instances.
Wow.
Yeah. And that involved 154 unique CVEs, or common vulnerabilities and exposures.
Okay, so before we dive into the juicy numbers, we have to define two key terms. The report splits the world into two groups, and this distinction is, well, it's everything.
It really is. It frames the entire security discussion. So they categorize the whole ecosystem based on real usage patterns. We're talking about what customers are actually pulling into their production environments.
And those two groups are?
First, you have the top 20 projects. These are the big ones, the most popular, most frequently pulled images, your household names, if you will.
And then there's everything else.
Everything else. The vast, sprawling majority of other images. And they call this the long-tail projects.
So if we connect this to the bigger picture, the paradox just jumps right off the page.
It's a huge disconnect.
Engineering teams, and this is totally rational, they focus their time and energy on those high-visibility top 20 images.
Of course they do. That's what they're measured on.
But the data reveals that the biggest operational and security burden lies squarely, overwhelmingly, in that neglected long tail.
It's a huge gap between the perceived risk, the high-profile stuff, and the actual operational exposure that teams are facing every single day.
And this deep dive is all about understanding the mechanics of that disconnect.
Let's get into it.
So let's start where the usage is highest. What is everybody running? The report pretty much confirms that modern infrastructure is built on a very consistent set of default production building blocks.
Yes, that's right. When we look at the global usage stats across their customer base, you see the foundational languages and runtimes that you'd expect. But the scale of dominance, especially for one particular language, is, well, it's really significant.
And that would be Python.
Python. It is the clear global favorite. It's used by 71.7% of customers.
71.7%. So that's nearly 3 out of every 4 organizations running it in production. That's massive.
It's huge. And then right behind it, you have Node as the next most popular language at 56.5%. Then you start getting into the core infrastructure components.
Things like Unjinx, I assume.
Exactly, and Jinx is at 40.1%. Then you see Go at 33.5%, and Redis, which is used for, caching and database support, that's at 31.4%.
So those five are really the anchors of the modern stack.
They are the anchors, but the list expands really quickly from there into all the necessary support components, things like JDK and JRE for any Java environments, obviously.
Of course.
And then this comprehensive suite of what you call cloud-native observability and platform tooling.
So we're talking about things like Grafana and Prometheus for monitoring.
Yes, and all the critical orchestration pieces. Istio for your service mesh, Cert Manager for handling certificate lifecycles, Argo CD for continuous deployment.
Ingress Jinx for external access, and Cube State Metrics to monitor the health of the Kubernetes cluster itself. It's the whole ecosystem.
It is the whole ecosystem, and what's crucial here is that this isn't just some generic list of tools. This is the full integrated portfolio you need to operate a secure, scalable cloud environment today.
And that huge number for Python usage, that 71.7%, it gives us a massive clue about what's driving this entire stack.
It absolutely does. That number isn't just about general purpose programming anymore. It's a signal. It signals that Python has formally established itself as the default glue language for the modern AI stack.
The AI stack.
Yes, and this trend is actively reshaping the baseline components that you need for any serious production environment.
So why Python? I mean, there are lots of efficient languages out there. What makes it the chosen one for AI specifically? And why does that choice matter for the rest of the software supply chain?
Well, it really comes down to two things: ecosystem maturity and standardization. Python has this just unparalleled collection of libraries. Think about PyTorch, TensorFlow, Pandas, SciPy.
All the heavy hitters for data science and machine learning.
Exactly. They're indispensable for model development and data manipulation. So when an organization decides, okay, we're going to build, train, or deploy an AI model, the path of least resistance is Python.
And it's where the talent is.
It's where the talent pool is, absolutely. So it starts out in the research and development phase, but then it very quickly moves into the production environment.
And that's where it starts to affect everything else.
That's right. The report details how this centralization works. Python becomes the standard for that initial model development. Then it's used to build the data pipelines that feed those models. And now, increasingly, it's being deployed for production inference services.
So the part of the application that's actually serving predictions to customers.
The part that's customer-facing, high stakes. And when those AI applications move from just being an experiment into a core part of the business, Python's central role forces every other component in the stack, the OS, the networking layer, the monitoring agents, to support it seamlessly.
It pulls everything else into its orbit.
Perfectly put. It pulls everything into its orbit.
That makes so much sense. If your core business differentiator is suddenly an AI service, well, then Python becomes your new default language. It doesn't matter what your legacy systems are running on.
And that leads us directly into the regional nuances, which is where things get really interesting. Because while that foundational language layer, might be dictated by these huge global trends like AI, the operational tools that surround that layer are highly dependent on the maturity and the history of the regional market.
So here's where it gets really interesting. The report compares usage across North America versus outside North America. And they show similar foundations, but a very different portfolio mix. It kind of hints at different cloud-native strategies.
The core stack is consistent, right? Python, Node, and Jinx, you see that everywhere. That's to be expected.
But in North America, while customers are using those core components, the report notes meaningful usage of utility images, specifically BusyBox.
Right. And alongside BusyBox, you see a really strong penetration of specialized Kubernetes ecosystem components, things like Node Exporter and Kubectl.
Okay, so BusyBox is this tiny consolidated suite of Unix utilities. Seeing high usage of that alongside tools like Kubectl and Node Exporter in North America, it suggests a really deeply integrated, highly mature Kubernetes user base.
I think so.
They're reaching for these low-level small utilities, not just to run their app, but to actively manage, debug, and really intensely orchestrate their container layers.
You've hit on a critical point. It signals a culture of sophisticated platform engineering. You have developers and SREs who are actively optimizing their runtime environment.
They're stripping down the base OS images, to the absolute bare minimum.
To the minimum, and then relying on tools like BusyBox for diagnostics and troubleshooting inside those heavily optimized containers. That level of granular control is really typical of markets that have been running Kubernetes in production for years and years.
Okay, so now let's compare that to the usage patterns we see outside of North America.
Right. So when you look beyond North America, the core stack is still there, but the application portfolio spreads out in a different way. You see a very noticeable presence of .NET runtimes.
The Microsoft ecosystem.
Microsoft ecosystem, specifically ASP.NET Runtime, .NET Runtime, and the .NET SDK. They show up really prominently, and they also see significantly higher usage of PostgreSQL in their core list.
That portfolio shift, the heavier reliance on .NET, it speaks volumes about the state of enterprise modernization in those regions.
It absolutely does.
Yeah.
It suggests that outside of North America, there's a stronger reliance on these large, established enterprise workloads that historically used Microsoft-centric technologies.
And now they're trying to move those to the cloud.
They're now containerizing their .NET applications, migrating them to modern cloud infrastructure, but they can't just abandon those mission-critical systems.
So they're forced to run this much broader, more complex portfolio that has to bridge the legacy systems, the .NET stuff, with the new cloud-native infrastructure like Python and Node.
Exactly. And the implication here, regardless of what region you're in, is profound. Modern infrastructure isn't some singular, uniform stack.
No, it's a highly diverse and customized portfolio of critical building blocks. Whether you're debugging with BusyBox in North America or you're managing a containerized .NET app in Europe, these components together, they form the irreplaceable, essential foundation of a business.
And that portfolio complexity is the engine that drives this next major point. It's the long tail. What customers actually run in production is far, far wider than just those top 5 or 10 names.
And that breadth is where the real complexity and the risk is hiding.
That's right.
Which brings us directly to the scale of this problem. I mean, if the top 20 images are so universally popular, how much of the operational reality do they actually represent? Let's talk about the size of this crucial long tail, the hidden half of production usage.
This is the section of the report where the data starts to get really counterintuitive. It challenges that traditional security focus. The usage patterns they defy the expectations of linearity.
So let's look at the numbers again. The report says that the most popular images, that entire group of foundational components we just talked about, the top 20, they represent only a tiny fraction of all the available images in the catalog.
And that fraction is 1.37%.
1.37%. So think about that. Less than 2% of the entire image catalog gets all the visibility, all the community attention, and all the security resources.
But what do those top 20 images account for in terms of actual daily production usage? That's the key question.
And the answer is, they account for roughly half of all container pulls across the customer base. So that tiny 1.37% of the catalog represents about 50% of the volume.
And that, by definition, means the other 50% of production usage has to come from everywhere else.
It comes from the long tail.
It comes from the long tail.
And that is the critical pivot. That other 50% isn't just spread across thousands of unused, orphaned images that nobody cares about. The report quantified it.
They did. 1,436 long-tail images are responsible for that remaining half of all production usage.
But the really key metric for an organization isn't just the pool volume, it's the size of their portfolio.
Exactly. And these 1,436 images make up a staggering 61.42% of the average customer's total container portfolio.
Let me just repeat that. Over 6 out of every 10 images that an organization relies on are outside that popular, well-maintained top 20 list.
It's a huge number.
I really want to dwell on that 61.42% figure for a second. It fundamentally changes what we mean when we say core infrastructure. These long-tail images might be niche, they might be pulled infrequently, maybe only once a month during some specific build process.
But they are absolutely crucial to the customer's operations. They are running in production. They are not edge cases you can just ignore.
So what kind of things are in this long tail?
Oh, it's a vast mix. It includes, specific versions of monitoring agents, highly specialized developer tools, maybe internal application proxy layers, database connectors for niche cloud services.
And I bet a lot of legacy internal utility binaries that some engineering team inherited and just hasn't gotten around to replacing yet.
Absolutely. The fact that they are pulled and used means they are often single points of failure for very specific business processes.
So let's think about the operational burden that this creates. Maintaining that top handful of images, Python, Node, and Jenk, the report says it's relatively straightforward.
And it is, because the community and the vendors are constantly focused on them. You get security patches frequently, they have high velocity.
But the definition of trusted open source has to extend to maintaining security and velocity across the entire breadth of what customers actually run.
That's the challenge. And that breadth is 1,436 different images, all with their own set of dependencies, often built on older OS layers, and often using components that get little to no dedicated community security scrutiny.
So the engineering team, they have a finite amount of security time. They look at their budget and they say, okay, we have to prioritize. We're going to focus our internal hardening efforts and our security audits on Python because that's our 50% volume driver.
And that is the strategic mistake that this data highlights so clearly. The long tail is precisely where most engineering teams lack the time and the specialized resources to manage.
They're spending their limited security bandwidth on that high visibility 1.37% of images.
Leaving the vast majority, that 61% of their image portfolio, largely unmanaged, unpatched, and potentially containing years of unaddressed security debt.
And this debt just accumulates quietly, hiding in the shadows of the long tail until it becomes this overwhelming operational risk.
It's the perfect analogy.
If the top 20 are the superstars that everyone pays attention to, the long tail's like the road crew. They're essential for the show to go on, but nobody knows their names, and they're doing the majority of the invisible, difficult work.
And that lack of visibility is why this next section is, I think, the most shocking part of the report.
Right. Now we pivot from just usage patterns to actual risk exposure. And this is the central finding of the entire deep dive. This is the moment that should redefine how you think about software supply chain security.
The conclusion is just so stark. Popularity does not map to risk. The data is unequivocal that the risk is overwhelmingly concentrated outside of the most popular images.
It's in the long tail.
It's in that long tail that is so difficult and costly for internal teams to maintain.
Okay, let's lay out the precise scale of this issue for everyone listening, because these numbers are just staggering. Out of all 10,100 CVE instances that were remediated during this 3-month window,
the top 20 images accounted for only 2% of the total.
2%, that's just 214 vulnerability instances.
And conversely, the long tail became the genuine center of gravity for security threats. The report found that 98% of remediated CVEs.
98%.
That's 10,785 CVE instances occurred in the long tail.
I need to pause on that ratio. We are talking about 50 times the number of CVEs found in the top 20 projects.
50 times.
So if your security team's focus and budget follows the frequency of usage, the volume of polls, they are directing almost all of their resources to managing just 2% of their actual vulnerability exposure.
It is the ultimate illustration of misallocated security resources, and it just exposes the fallacy of relying solely on internal manual patching efforts.
The implication is severe. The biggest security burden accumulates in the less visible part of the stack. The necessary patching and vulnerability management is hardest to operationalize exactly where it's needed most.
Exactly.
But I do get the developer's rationale. It's rational, as the report puts it, for engineering teams to focus on the core few projects. Python, Node, their own business-critical application code. Those are the systems they own and are directly responsible for.
Of course it's rational. If you have limited time, you focus on the crown jewels. But the consequence of that rational focus is that the vast majority of your exposure, that 98% of risk, sits in the dependencies they didn't write.
Components they don't fully understand.
And they certainly don't have the time or the specialized knowledge to meticulously track, update, and then test for regression errors. This is dependency inertia in action.
So let's dig a little deeper into the nature of these vulnerabilities. The report says that the largest volume of CVEs they tracked were categorized as medium severity. Now, when we talk about security urgency, teams are usually scrambling to fix the criticals and the highs first. So why should a huge volume of medium CVEs in the long tail be so concerning?
This is a really high-value insight that often gets overlooked. A single critical CVE in a core high-visibility image like Noon Dreams is catastrophic, of course, but it's typically identified immediately by the community and it gets patched within days. Teams expect to drop everything and fix it.
It's the fire drill that everyone is trained for.
Exactly. But the long tail volume is a different kind of problem. A high volume of medium severity CVEs, especially in these obscure low visibility components, suggests a chronic underlying lack of maintenance and scrutiny.
So what are these mediums used for by attackers?
Well, medium severity vulnerabilities are often used for things like reconnaissance, information gathering, privilege escalation, or as part of a chain attack. They are the footholds that attackers use to move laterally once they're already inside the perimeter.
So a high volume of mediums in the long tail is a sign of long-term operational neglect that just compounds the risk over time.
Precisely. If you have 1,400 long-tail images, and each one has 5 medium vulnerabilities that have gone unpatched for 6 months, that's 7,000 potential entry points that never trigger a security fire drill.
And these medium CVEs, they act as this hidden landscape of soft targets.
They do. And they dramatically increase the complexity of any potential exploitation chain. For an attacker, it's far easier to find one obscure, unpatched medium vulnerability in some deep dependency than it is to find a 0-day in Python.
What's so fascinating here is that this concentration of risk in the long tail creates this profound psychological and operational disconnect. Developers are focused on their primary tools, which are generally well-maintained and relatively secure.
Yet the vast majority of their security exposure truly resides in the obscure secondary and tertiary components that make up the bulk of their infrastructure portfolio.
We used the analogy before of locking the front door, but let's expand that. Imagine you run a massive factory. You've invested heavily in fire suppression systems for the main assembly line. That's your Python and Node applications.
Right.
But 60% of your factory space is this dark, dusty storage annex filled with old machinery. And 98% of the electrical hazards, the loose wiring, the flammable materials, are hidden back there, accumulating unseen.
The operational urgency is focusing on the assembly line, but the existential risk is in the annex.
And the challenge for organizations is realizing that they need a mechanism to secure that factory annex with the same rigor and speed they apply to the main assembly line.
Because the security battle is being lost in the long tail, manually keeping up with 1,400 projects is just functionally impossible.
Okay, so given that this problem seems almost intractable for internal teams, what external forces are compelling organizations to finally address the full depth of their stack? Let's shift our focus to compliance. The report suggests it's becoming a crucial catalyst for action.
I think that's right. Compliance is no longer just a burden, it's an operational mandate that's driving necessary security improvement.
Advanced everywhere.
Everywhere. We're seeing comprehensive requirements emerge from detailed SBEM mandate software bill of materials to stringent vulnerability disclosure requirements. And that's alongside formalized industry frameworks like PCI DSS, SOC2, and major international regulations like the EU's Cyber Resilience Act, or CRA.
And all of these frameworks, they mandate a higher level of security assurance across the entire supply chain.
They do, and the report uses FIPS, the U.S. federal encryption standards, as a primary and I think really compelling example to illustrate exactly how this regulatory pressure drives broad adoption and hardening across the entire supply chain, and that includes the long tail.
So FIPS, that's the Federal Information Processing Standards. It's all about cryptographic modules, right?
That's right. FIPS 142 and 143 require rigorous testing and validation to ensure that sensitive data is protected using verified encryption. For any organization dealing with U.S. federal clients or government data or even sensitive healthcare info, FIPS compliance is non-negotiable.
So it provides this clear, high-contrast window into how quickly and broadly teams will adopt hardened components when they're mandated by an external authority.
Exactly. And the adoption rate they found is extremely compelling. 44% of Chainguard customers run at least one FIPS image in production.
Wow, that's approaching half their customer base. They're actively dealing with government-level cryptographic compliance.
And when you look at which FIPS images are the most used, they align perfectly with the broader popular portfolio we talked about earlier.
So the compliance requirement doesn't introduce new languages. It just forces the hardening of the ones they already rely on.
Precisely. It's the same core set of foundational languages and tools, simply with the cryptographic modules strengthened, audited, and verified for these high-stakes environments.
So the requirement doesn't just stop at securing a single custom application written in Go. If that Go application relies on a network proxy or a cache, those components must also meet the FIPS standard, even if they fall outside the immediate scope of that primary application.
That is the crucial insight. Compliance demands a recursive level of trust. The report lists the top FIPS images run by customers who use at least one FIPS image, and it just confirms this mirroring effect.
What are the numbers?
Python FIPS is used by 62%, Node FIPS is at 50%, and Jinx FIPS at 47.2%, Go FIPS at 33.8%, and Redis FIPS at 33.1%.
Those numbers essentially demonstrate the cascading nature of compliance. If you need FIPS for your Node app, you almost certainly need it for your data processing pipeline in Python, your web gateway in Nginx, and your caching layer.
And that mandate extends deep into the platform tooling that makes the whole cluster function. They also see usage of supporting components like Istio Pilot FIPS, Istio Proxy FIPS, Cert Manager variants.
And even foundational OS components like glibs open sample FIPS.
Right. This proves that achieving compliance isn't just about updating your application code, it's about validating and hardening every single component in the dependency tree.
This raises an important question then. What does FIPS adoption teach us about securing the general state of trusted open source, especially when we think about that long tail problem?
It illustrates a universal, unavoidable truth. When you're operating within these stringent compliance frameworks, whether it's FedRAMP, DoD-IL5, PCI DSS, SOC2, or the upcoming CRA teams absolutely need hardened, trusted open source across the entire software stack.
Compliance demands breadth and rigor.
It explicitly does not allow for the neglect of the long tail, because the chances are high that some obscure long-tail utility image is running an unverified, non-FIPS cryptographic module somewhere deep in its dependency tree.
So compliance becomes the necessary leverage. It forces organizations to invest in securing components they might otherwise deprioritize. It shines a light directly into that dusty factory annex we were talking about.
Exactly. Compliance mandates external accountability. And that accountability is the only thing powerful enough to force organizations to address the 61% of their image portfolio that contributes 98% of their risk.
It forces them to look for providers who can deliver hardened, secure versions of everything they rely on.
Not just the top 5 images. Everything.
Okay, so we've established the severity of the long-tail risk, and we know that compliance is pushing organizations towards solutions that can address it. The final piece of this puzzle, and maybe the single most important metric for establishing a true baseline of trust in a supply chain partner, is remediation speed.
It has to be.
The question isn't just if you can fix a critical CVE, but how fast.
Right. In this highly dynamic environment, trust is measured almost entirely as time to fix, especially for those critical CVEs. The ultimate test of a trusted open source provider is whether they can achieve an operational speed that meaningfully outpaces the threat landscape.
And critically, whether they apply that speed universally, including to the long tail.
That's the key.
The performance metric shared in the report here is, it's genuinely remarkable. Chainguard eliminated critical CVEs, on average, in under 20 hours during this analysis period.
Let's put that into perspective. The traditional organizational time to fix for critical vulnerabilities is often measured in weeks or, horrifyingly, months. The industry average for patching a critical vulnerability can easily exceed 45 days.
Especially for components that aren't Python or Nginx.
Exactly. This report details a system where 63.5% of critical CVEs were resolved within 24 hours.
And the velocity just continues from there. They pushed it further, with 97.6% resolved within 2 days.
And a full 100% resolved within 3 days. That is a near-perfect response rate.
How is that kind of speed even possible?
It's achieved by industrializing the patching process. They're operating well inside their own established SLAs, their service level agreements, which are already robust at 7 days for criticals and 14 days for high, medium, and low.
So beating your own aggressive SLA by such a wide margin is the signature of a fully automated, streamlined process.
It has to be.
And their speed wasn't just limited to the most urgent critical category, which is often where vendors focus all their energy for, PR purposes.
Not at all. And the consistency across all the severity levels is what proved the automation is robust. They detailed the remediation speeds for the other categories too. High CVEs were addressed in 2.05 days, mediums in 2.5 days, and lows in 3.05 days.
So this demonstrates that vulnerability management isn't a series of panicked manual fire drills.
No, it's a systematic automated flow that processes all threats with extreme velocity.
Okay, now let's connect this exceptional speed back to the strategic long-tail problem. This is where the real power of this data lies for you, the listener.
Right. We established that 50-to-1 ratio earlier. For every single CVE remediated in a high-visibility top 20 image project, 50 CVEs were resolved in the less popular long-tail images.
So this speed wasn't just applied to securing Python.
It was applied to securing those 1,436 obscure utility images that form 61% of a customer's portfolio.
So what does this all mean for the organization that's struggling with that overwhelming operational burden?
It means the bulk of their real security exposure, those 10,785 CVE instances residing in the quiet majority of their images, is being secured with the same rigor and lightning speed as their most critical workloads.
This is the operational transformation. The average developer cannot spend their time chasing down an obscure vulnerability in a utility image they only use once a quarter.
They just can't. But if that vulnerability is fixed, tested, and shipped in a new, clean image in under 20 hours automatically, the operational burden just vanishes.
The service absorbs the massive, unmanageable debt that individual engineering teams simply cannot afford to allocate time toward.
It transforms the entire risk profile. Instead of the long tail being this source of constant, invisible accumulation of risk, it gets integrated into a system of continuous high-speed remediation.
And this level of industrialized security is the only mechanism that makes managing that vast long tail feasible today.
It allows engineering teams to return to their core mission, which is building applications, rather than fighting this perpetual losing battle against dependency churn and vulnerability management across a portfolio of thousands of images.
So trust in the software supply chain isn't built on finding flaws.
No, it's built on eliminating them with verifiable speed and breadth.
Okay, let's bring this all together.
To synthesize everything we've uncovered, I think the major takeaway is this. Modern software infrastructure relies on a wide, shifting, and highly customized portfolio of open-source components. And that portfolio is heavily influenced by massive trends like the rise of AI.
And the vast majority of those components, over 61% of an average customer's image portfolio live outside the top 20 most popular high-visibility images.
And this is the critical failure point for most organizations. Because developers rationally focus their time on those top-tier projects, the data confirms that 98% of the operational security and compliance risk accumulates in that vast, less visible long tail.
It's the factory annex, quietly accumulating debt.
It is. And for security and operations teams who are trying to maintain this manually, it often feels completely hopeless trying to keep up. The volume of images and vulnerabilities is just too high.
So this requires a shift in strategy.
It requires recognizing that a scaled, specialized solution is necessary to secure that quiet majority of the software supply chain. And compliance, through standards like FIPS, is proving to be a potent catalyst to mandate this comprehensive approach.
Absolutely. The core security philosophy suggested by this data is crystal clear. Breadth matters more than depth in a few select visible areas. The focus has to shift from securing only the most critical visible pieces to managing the entirety of the software supply chain.
Because the greatest exposure is hidden in plain sight. It's protected by the false confidence that high-profile packages are the primary target.
The concentration of risk is not uniform. The rational choice of focusing on the top 20, that 1.37% of available images, leaves organizations vulnerable to the 98% of CVEs that occur in the remaining 1,400-plus projects that constitute the bulk of their actual infrastructure.
Which demands a capability to fix everything, everywhere, fast.
So we'll leave you with this final provocative thought to explore on your own. If 98% of vulnerabilities hide in images that represent 50% of your production container pools, how accurately can your organization truly measure its overall security posture if you only scan and patch the top 2% of projects?
What hidden critical business processes, a monthly financial reconciliation, a specific utility for deployment, a legacy enterprise database connector, what relies on that single, obscure, and potentially long unpatched image in your long tail?
Ignoring the long tail means allowing the majority of your security exposure to be dictated by components you don't even know exist.
Food for thought indeed. Thank you for joining us for the deep dive.
We'll catch you next time.